What contributes more to climate change than all of the world's planes, trains and automobiles combined? Farm animals. According to the UN, raising animals for food is one of the largest contributors to greenhouse gas emissions. And that's only the beginning. As demand for animal products has grown, animal agriculture has gobbled up more and more water, energy, crops and land. Everyone from leading water and climate scientists to Oxfam and World Vision, and even the United Nations agree that by eating less meat, we can reduce pollution, save resources, and combat world hunger.
Our design was mainly motivated to be sustainable, to be efficient, and to be easy for the user to maintain. So our main goals were to use less water, so our system doesn't need daily watering. The water is held in this reservoir and it's pumped up to the top of the system and then cycles through, so the water is constantly being recycled. And the system doesn't use any soil, so there's no soil or fertilizer on the soil that could possibly run off into other water sources, and our system is completely maintained. One of the benefits of hydroponic gardening is that a higher yield of whatever you're growing is produced, and that's difficult to measure in the time span that we have. But just from a space standpoint, the vertical design of this system, you would be able to plant more crops in a smaller space using this sort of design. So we're maximizing the use of a small space. And for the user-friendly aspect, this whole design you could put indoors, and you can easily refill the water into this reservoir, and it's easier to test pH in water than it is in soil, so you can be sure that you're providing your plants an optimum growing environment. So for our design, it does need to be plugged in because the pump is constantly running to provide the continuous flow of water. And the pump leads into this PVC tube, which is held in place by a 3D printed component. And the basil plants are suspended in root cups that are basically netted cups that allow for the roots to hang into the water. And the plants are supported by chopsticks just to allow them something to hang on to. And then rocks are also added for more stability. And the downspouts are sloped, but just a slight slope so that the water can run through by gravity, but the plants aren't disturbed by it. And for the reservoir, the water can be easily refilled, and it's very easy to collect samples to test the pH.
We used the pH sensor and the spark plug kit to test the pH of the water and compared it to the tap water. Here is our wired up diagram. The pH probe is submerged into the solution with pH 4, 7, and 10, which come from the pH sensor package. The readings are recorded by running the Arduino. The calibration curve is made with the collected data. The graph is showing that the R-square value is 1, which means the data collected is accurate. Then we use the same setting to test the pH of system water and tap water we collected for the past 10 days. By averaging the running data, we made a graph of pH of the tap water and system water with MATLAB. When we are recording the data on the 5th day, we found the pH is continually dropping, so we added hydroponic solutions in the water tank to maintain the pH. The rate of pH dropping slowed down effectively. For basil, the appropriate range of pH for it to grow is 5.5 to 6.5. Our data remained in the range in these 10 days. In conclusion, the system with running water is supporting the growing of basil.